Oh, I see. I'm using a new audio output. Okay. All right. How about now?
Let's try again.
Yeah. Okay. Awesome.
All right.
Perfect. All right. So now people hear. Yeah, I'm using a new. I had to remove one of my audio devices. Okay. All right. So now people just tell me that you can hear the guest, although I think I can see the little line moving that says that you should be able to hear the guest. So I apologize to do this, but we're gonna have to do this all over again. So who are you, and what do you
All right.
do?
Yes. So I'm Markus. I'm a professor of astrophysics at Stockholm University. I work with exoplanets, basically anything that interests me at the Max Planck Institute there. So that was, I took it in 2008, started my PhD in 2005. So that was sort of when people started trying to directly image planets, which is really sort of the bulk of what I do. And then, as you mentioned, I was in Toronto for 3 years at the University of Toronto, and then in Princeton, and then a bit of a séjour in Belfast as well. And now I'm in Stockholm,
Right.
in Sweden, where I grew up.
So and so how you came to my attention is that you published a paper about a fascinating idea of connecting a starshade to ground-based observatories, and that sort of tickled a whole bunch of my sort of check boxes there. So let's just talk about just this idea of what a starshade is first, and then we'll sort of talk about how it could be adapted to ground observatories.
Absolutely. So yeah, I mean, if we go even sort of just one step back to set the scene a little bit, obviously, if you're trying to image a planet, which is what we want to do, a big problem that you have is that the planet is faint and it's very close to a very, very bright star. So the brightness distance difference between the planet and the star, if you're thinking about an Earth-like planet, say around the Sun-like star, that contrast, so the difference in light between the planet and the star is about a factor of 10 billion. So that's obviously a big difference, and that means that the light, the very faint light that's coming from the planet, very easily drowns out in the more, much more intense light
Yeah.
of the star. So you have to deal with that in various ways. And the way that people have dealt with it classically is with a so-called coronagraph. So you're basically you're putting in your instrument, which is meant to block out the light from the star physically, but not block out the light that's coming from around the star, so that you don't miss out on the planets. And so that's a good way of doing it. It's a technique that's been developed over decades by now, and people have come up with great ways to do that. But it has certain limitations. Among other things, it puts very, very high constraints on the quality of the optics in your telescope, for example. And even then, it's even if you can achieve that, there are other difficulties. It's
Right.
very hard to make it very broadband so that you can cover a wide range of wavelengths at the same time when you're taking, because what you want to do in the end, right, is you want to see these planets, and then we want to take their spectra.
Right. And,
Um,
and so like just having a really powerful telescope, like if you had the most powerful possible telescope and you pointed it at some nearby star system that you knew there were planets, if you just took your telescope, pointed it at the star system, you couldn't reveal the planets because just the light from the star is just too bright.
exactly. I mean, if you had like an imaginary telescope that was really, really enormous, then at some point you will reach the point where you get small enough stellar leakage that it's not going to affect the planet. But that's really a fantasy telescope.
Right.
If you want to do this in reality with real telescopes, then yes, you're not going to see anything. Like if you imagine like the whole solar system at a few tenths of light years, which might be what we're talking about. I mean, and you try to take an image basically out to Neptune or something like that, covering the whole system. I mean, the whole field of view
Right.
would be white, basically,
Right.
because
So
of
if you can like zoom
the
in just to the point that you only look at the planet, then you're okay. But if
yeah,
there's any star in there, you're not going to be
yeah,
able to see it.
exactly. You're sensitive enough to see the planet if it was as bright as it is and was isolated, but when it's next to the star, it just drowns out in the noise that leaks from the star.
Right. Okay. Doing it on the telescope itself.
Exactly. So basically, you put this item. I mean, as you say, there are lots of ways to do it. And it's inside of the telescope, so it's basically behind your primary mirror, and that means that it's affected by the diffraction properties of the telescope. You can't escape that fact if you put your chronograph inside of your telescope, and that leads to all of these constraints that I was talking about. That you really need a very, very good telescope to do this. And you need lots of other things to be right as well. I mean, we haven't even touched on the fact that we want big telescopes to do this, which means that by and large, we're really tied to the ground because it's very expensive to launch these huge telescopes into space. And that means that we have to deal with the atmosphere, which is a nightmare because that messes up the wavefronts of the light. So if something would look like a very nice point source, if you looked at it, without an atmosphere, you mix in the atmosphere, it's a big blobby mess, right? And that's much more difficult.
But I mean, with the latest, with the existing telescopes, say the extremely large telescope, or sorry, the very large telescope, the Keck observatories, the Gemini, they have the adaptive optics to be able to partially deal with the disturbance of the atmosphere, but not fully, not to the same level as a space telescope.
Exactly, indeed. So basically, if you use adaptive optics, and basically this is the technology that I alluded to that made it possible in sort of the mid 2000s to actually start to image some exoplanets, and this is adaptive optics. So basically, correcting for what the atmosphere is doing by changing. So the atmosphere is basically imposing distortions on the light that's coming in. And so you have your telescope, and in your telescope you place a mirror that can change its shape. And so you try to monitor what the atmosphere is doing, and then you try to change the shape of the mirror,
right?
In order to exactly compensate for what the atmosphere is doing, and that gives you a much better spatial resolution. So then you can start to image some planets, like giant planets, which is what we can sort of do today. But it's still too difficult to image sort of Earth-like planets, for example.
And I mean, we've seen some of the really incredible images coming out of, say, the Very Large Telescope and the Espresso instrument in infrared, revealing newly forming planets, multiple planets around star systems. And that's great, and it's mind-bending, but it's not the same thing as looking at a sun-like star and seeing an Earth-like planet with a blue ocean, etc., orbiting around it. Like that's what we really want to see.
Exactly. I mean, that's what we're working towards, right? It's of course there's lots and lots to learn about these planets that we can see, and of course we're doing that work as well. Trying to understand how they form, which will also inform us of how Earth-like planets form and so on. But indeed, I mean, what I think it's fair to say that everyone who works with exoplanets, what they really want to achieve is to really study truly Earth-like planets. And especially, if you can see an Earth-like planet around like a sun-like star, where you're really looking at something like home, right? Or that's potentially like home, like
right.
A place that we know and where we know that life, for example, could thrive.
And so thanks to this power of adaptive optics, potentially the interferometry of putting multiple telescopes together, say with a very large telescope, the power of ground-based observatories is really starting to match and even exceed the capability of the space-based observatories, but still it's going to suffer these problems of the atmosphere. So what are the, so let's go back to this idea then of the Starshade. How does the Starshade work in helping to find planets?
Yeah, so basically the Starshade then, in contrast to the coronagraph, is something that you put outside of the telescope, and you have to put it at a very large distance away from the telescope for the optics to work out. But basically, it's basically what it sounds like. It's a sort of black thing that you put in front of the star. So basically, you put it between your telescope and the star that you're looking towards, so that it blocks out the light from the star, whereas planets, the light from planets can sort of get through around the edges of this starshade. So, like the most intuitive thing that you might want to do is just to use like a round shade and put that between your telescope and the star. But that doesn't actually work because of diffraction. You get diffraction of light around the edges of the starshade. So what you do instead is you give the starshade like a funny shape. It kind of looks like a flower with petals going out from the center. And that helps you not diffract light. It cancels out the diffracted light to a sufficient degree that you can actually get to these contrasts that you need, where you really block out enough of the starlight.
And how much of that light are you blocking out? Like how many orders of magnitude of light are you attempting to shade with this thing?
Yeah, so basically what you're aiming for, right? Because as I said, everyone here in this game are aiming for 10 billion.
1 in 10 billion. And so the star is 1 in 10 billion, or to be able to even see the planet, you've got to be able to let in 1/10 billionth the light of the star while blocking the star itself.
Exactly.
Yeah.
So that tells you got to have an extreme precision to do that, right? I mean, to really not make a mistake with any of these 10 billion photons.
Right. And so these starshades, I mean, these ideas have been around for probably about a decade now, and people have been proposing to fly them either as special exoplanet hunting missions on their own, or maybe even having them be a follow-on mission. I know people have thought about using them for James Webb. I've seen proposals for using one for the Nancy Grace Roman telescope. But you're suggesting that, in fact, they could be used for a ground-based observatory.
Indeed. So I mean, it's exactly as you said, right? There are all these space missions where you have a starshade in space and you have a telescope in space. And you do exactly what we said, right? You put the starshade between the telescope and the star that you're trying to observe. Yeah, that's great, because then you have your telescope in space, so you don't need to worry about a lot of things like the atmosphere and things like that. But you do have to worry about the thing that the aspect of actually sending a big enough telescope into space that you can actually get something out of the light that you're then receiving from the planets. So the telescope has to be big enough, and that's really a sort of a limitation if you're working in space. So the idea that I developed starting in 2007 during the time of my PhD was to actually have your starshade in space, but relay the shadow of that starshade onto a spot on the ground where you have your telescope. So you're letting your telescope stand in the shadow that you're casting with the shade. Which, if you don't need to think about it for very long to understand that that's a geometrically difficult problem,
right?
Because if you're thinking instantaneously, okay, at one given point in time, sure, I can place an occulter here, and I can have my telescope standing where it is on the ground, and everything will line up. But then, in the next instance, the Earth will have rotated
and moved
around its axis. So the telescope is now in a different place from where the shade is, and your shade, you can't keep your shade fixed in space. It's forced to move on a Keplerian orbit in some sense, and so that will also move out of where it was one instant ago. So basically, the trick of the game is to try to match the movements that the occulter is doing in space to the motion that the telescope is undergoing as the Earth is rotating for long enough that you can maintain this shadow stable, so that you can use the telescope for the observations that you want.
And so how long do you need to be able to make an observation?
Well, the nice thing about this, right, is that as I said, you can work with potentially really, really big telescopes like the ELT, for example. And so that means that you can actually, basically the longer that you want to hold the shadow, the harder it is. I mean, you could hold it for many hours, but it would take a lot of fuel, basically, because you have to make corrections to the
Right. I see.
orbit of the starshade all the while you're doing it. So that's harder the longer you go, and that means, for example, that if you spend all this fuel standing fixed on one target, maybe you don't have any fuel left to do the next target or whatever. So it becomes a difficult fuel budget problem. However, fortunately, if you're using a really big telescope, you don't actually need that much time. You don't need it to keep it fixed for a very long time. Like the ELT, for example, could see an Earth-like planet in a matter of a minute or something like that. So you really only, in principle, need to keep it fixed for a few minutes, depending on what you want to do, of course. If you then want to take a spectrum, you want to stay on it for longer and so on.
And so which orbits would work with this configuration? I mean, I'm imagining you've got your ground telescope. Obviously, there's like the geosynchronous orbits, which would keep the Starshade roughly above the telescope at all times. But would that do the trick for you?
No, because you then have basically a fixed axis between the Starshade and the telescope on the ground. So that's one part of the problem. But then the next part of the problem is that when the Earth then rotates, your star is still in that direction.
Right.
But the whole axis has now rotated with respect to that frame of reference. So that means that your Starshade and your telescope are perfectly lined up, but not on the star,
right,
on some completely different part of the universe. So that doesn't do it. Basically, there are two known classes of orbits that can do it, that have been sort of shown to work in theory, of course, but we understand the physics of orbital dynamics very well. So they most likely work also in reality. So one is basically if you have the Starshade in an Earth trailing orbit at a certain appropriate distance from the Earth. An Earth trailing orbit, by the way, is not a stable orbit. So over time, you have to make little corrections to actually stay in this Earth trailing orbit. But it's actually that requires a very small amount of fuel relative to all the other operations that you have to do. So that's not a big issue. So you can do that and basically both keep the Starshade stable on a given target for a certain amount of time, and then being able to move on to another target with some small sort of corrections to what your occulter is doing at the right time, so that you can then observe another target and so on, moving forwards in time. A limitation of that is that with this Earth trailing orbit, basically, if you wanted to observe something that was at the celestial pole, let's say you wanted to observe the pole star, now you have a big problem because the pole star is in the wrong direction for this orbit to ever line up.
Right.
So basically, with this class of orbits, you're stuck to within something like plus minus 5 degrees of the celestial equator. So the celestial equator is the sort of, if you take the equator of Earth and you project that out into space, that's what we call the celestial equator. Now there's lots of nice stars within plus minus 5 degrees of the celestial equator, but of course it's not every star. For example, Alpha Centauri is a super interesting system. You could never observe it with these kinds of orbits because it's just not at the right place in the sky to do that.
Right. Now you were mentioning two orbits. So this is one, the Earth trailing orbit. What's the other orbit?
Exactly. So that was one class of orbits, and then the other class of orbits is a set of highly elliptical orbits. So the Earth trailing one was the one that I developed back in 2007. These elliptical orbits have been developed by John Mather.
Of course.
In the US.
Nobel Prize winning John Mather.
Indeed. So that then basically you're at a highly elliptical orbit, which means that the way elliptical orbits work is that so it's in an Earth-bound orbit. So it's sometimes very close to the Earth and sometimes very far from the Earth. And so basically, when it's very far from the Earth, because of how the velocities work, basically it moves very, very fast when it's close to the Earth, and it moves much slower when it's far from the Earth. So by having the right kind of eccentricity and so on, so eccentricity being how elliptic the orbit is. You can match up the speeds so that when it's at its basically farthest point away from the Earth, it lines up both in position and in velocity, such that you can keep the shadow in the right place over the telescope.
And would that let you get away from the plane of the ecliptic?
Yes, it would. On the other hand, it's more expensive in terms of fuel in that setup to change from one object to the next. So that means that for the same amount of fuel, you would probably get fewer targets with that, but you could choose which ones they were. So really, at the end of the day, if you wanted to make a choice between two orbits, between these two classes of orbits, it's going to be a question of, okay, what's the science case actually that you're looking for?
Right.
Are you looking for a few targets that you're really, really sure are very interesting? Then these elliptical orbits are going to be the best. If you want to have something more like a statistical survey or something, you want to observe more objects, but you can't really choose exactly which ones. Then an Earth-trailing orbit is preferred.
So I'm sort of imagining we take this Starshade, we roll it up, we put it in a rocket, launch it into whichever orbit has been decided by the Council of Scientists. It deploys this giant Starshade and it is now in orbit. Now, can it be used by multiple observatories, or is it just tied to one observatory?
It could be used by multiple observatories on Earth, but only one at a time. So, and you would need to know in advance which telescope you're going to use, because you have to far in advance be able to plan where the Starshade is going to be at any point in time. Right. So basically, and then it depends on a bunch of other factors. Like, for example, if you design your Starshade to work perfectly with the VLT, then you can probably make it work perfectly also with the Super Telescope or with the Gemini telescopes. You might have a difficult time getting it to work with the ELT, for example, because basically when you're designing the optimal parameters for the Starshade, one of those parameters that you're playing with is how big is the Starshade in diameter.
Right.
And basically, if you're using only a small telescope, then the shadow that you need to cast doesn't need to be that big. You don't need to make the Starshade that big necessarily. Whereas if you're going to make it work with a bigger telescope, you're going to need a bigger Starshade, so you cast a bigger shadow, because you need all of your telescope to be inside of the shadow.
Right. So roughly the size of the Starshade is tied to the size of the telescope.
Yes. So that's one aspect that ties the size of the occulter. The Starshade. I'm using the terms occulter and Starshade interchangeably. Another is basically another aspect has to do with what kind of contrast that you're actually aiming for, because the bigger the Starshade is, the bigger the contrast also, provided that the distance between the telescope and the Starshade is fixed. If you keep those fixed, then making the Starshade bigger will make your contrast deeper. Right. So basically, there's a trade-off in how big you make your Starshade. Now, by the way, because when I say it like that, people might wonder, well, why don't you just make the Starshade really big and get really great contrast? But the problem is that the bigger you make the Starshade, you also get a worse so-called inner working angle, which the inner working angle is basically how close to the star can you look for planets. And if you have a really big Starshade, then you're blocking off a really big part of the field of view, and then you won't be able to see many of the planets. So there's a trade-off there that you have to make.
Right. And so then, you talk about this idea of the fuel use. How much fuel will you be using to move to different targets? What's the lifetime limit, do you think?
Yeah, so basically, one of the tricky things about space, right, is that there's no friction or anything like that. You have nothing to push against. I mean, if you want to walk somewhere there where you can push against the floor, and that helps you get to where you want to go, or if you if you go in a car, you can burn fuel to make pistons move, and that will make your wheels move, and you can move forward. In space, you don't have those options. The only option really, well, that's the truth with modification, but in practice for these purposes, the only option that you have if you want to move in that direction is that you need to expel something in the other direction.
Right.
And preferably at a large speed, so that you can get a lot of momentum in that direction, which by conservation of momentum will get you moving in the other direction. So if you want to move a big mass in this direction, you don't want to preferably expel a huge mass in the other direction, because that will cost a lot. I mean, this is the fuel that we're talking about, right? It's basically the fuel is not really maybe the technically correct. Maybe you should call it propellant.
Propellant, yeah.
So you want to send that. You don't want to send too much mass. So you really want to send it in a high velocity, so that you can get a big momentum in the other direction. So basically, that's the only thing that you can do, and that means that you have to carry basically a lot of propellant with you in the end. And so, so for example, John Mather and his group have made a sort of detailed calculation about the fuel budget in their concept. And so in that, I don't remember the exact numbers because it was a while since I read the report. But basically, the dry mass of the occulter, and when I say dry mass, I mean the mass of the Starshade itself, not counting the fuel that it also has to carry with it, is I think something like 12,000 kilograms, which is a whole lot of mass.
That's a lot.
It's a whole lot of mass.
Yeah.
And it's meant to carry several thousand kilograms of fuel. And the way that works out, if you sort of think of realistic scenarios, it depends a lot on how you do things. But basically, that's enough to observe maybe 10 systems with their setup.
Now, one of in the chat, A.V. Scott and Flower just asked, why not use the Starshade as a light sail? So is there some way to do double duty where you could have it be a light sail?
That's an excellent question. And that's sort of why I said it's a truth with modification, that the only way that you can move in space is to expel something. Because another way, of course, to do it is to use the sun in one way or another, either by letting the light from the sun exert a pressure on your vehicle. And of course, if you have a Starshade, I mean, that's basically like a solar sail, right? It's a big flat surface, basically.
Yeah.
So it's kind of a natural way to think about it. Couldn't we use the pressure from the solar light to actually maneuver this thing? And unfortunately, you can't, because you just can't generate enough thrust.
Right.
I mean, the solar. I'm looking for the English word for what the solar light pressure, so to speak, is just not high enough, even though you have this big collecting area, to push such a big mass in the direction that you want fast enough.
So let's see. We've sort of talked about all of the engineering challenges and what it's going to be and how it all is going to work. But let's talk about the benefits. So what does a Starshade, working as an occulter for, say, the extremely large telescope, what benefit does that give that telescope?
Yeah, so basically you can, in terms of the telescope, it basically opens up a completely new range that you just cannot observe otherwise. I mean, basically, once you have blocked out this star, it's basically like you're looking at you have your huge telescope, and you're looking at free lights from this planetary system that's around the star. So basically, any planet that's around there that's reasonably bright, you're going to see it. The Starshade, once it's unfolded, it has very few moving parts. It needs to be able to use its engines to take it to different locations, but it's not, it doesn't need to have any other moving parts inside of it. So
right.
It becomes very robust to everything that can go wrong in space, which is a lot.
So like I know that, say, the extremely large telescope, which is going to be a 39-meter telescope, is equipped with a coronagraph, and so it is built into the telescope itself. So it is already, I mean, one of its science goals is to be able to look at sun-like stars and be able to detect the Earth-like planets around it. So this is the job and the work that it's already going to be doing. So I guess, taking spectra, it's going to be able to determine some of the chemical characteristics of these planets that are orbiting around these stars. So what additional benefit do you get from that Starshade? Because it sounds like you only get 10 shots, say, to super zoom into the planets around some star.
Yeah. So basically, it's correct what you say. So the ELT has a chronograph. It has, in fact, several planned instruments that will have very sophisticated chronographs. So one of the ambitions, for sure, one of the ambitions is to image planets. And you could say one of the ambitions also is to image Earth-like planets, maybe even in the habitable zone. And that is true, that is an ambition, but it is very challenging, and it's only really feasible for in very special cases. So, for example, if Alpha Centauri A or Alpha Centauri B has Earth-like planets around it, then you can probably detect them reasonably with the ELT. But there are a few sort of nearby so-called M-dwarf systems, like Proxima Centauri, for example, where you could do the same thing. But after that, you're kind of stuck because then if you go to even slightly more distant systems, you sort of run out of space with respect to what the ELT can do by itself. So, I certainly hope that Alpha Centauri has planets around it, because it would make our lives easier in so many ways. But we can't guarantee it, of course. And so if there are no planets there, then we're out of options. And in any case, that's just one system. And in the end, you want to be able to study much more systems in order to really say something about the prevalence of Earth-like planets and Earth-like planets in the habitable zone, and the prevalence of potentially even life in the universe. You can't just have one example.
And so, you talk about, say, Proxima Centauri, Alpha Centauri, so let's say 4.5 light years away. What feasible distance would like the raw extremely large telescope be able to observe out to? 10 light years, 20 light years, like at a certain point?
5 light years is basically the limit.
Really?
Of the ELT, in terms, if you're really talking, it depends on exactly what science case we're talking about.
Right.
So if you're talking about Earth-like planets in the habitable zone, you can't really go much farther than that.
And so you're going to really tap out with how far you can go with the extremely large telescope. And so then if we use the version with the Starshade, and I'm sort of assuming that TESS and Ariel and all of these different space and ground observatories have done all of the legwork. They've found all the promising candidates. They've been observed with James Webb. They've been followed on, and then you get like 10 shots of the best telescope, most powerful telescope humanity's ever built, matched with the best way to block the light. How far out does that give us?
So then you can go out to, and now I have to make the conversion. I can only think in parsecs, so I have to make a little bit of a
just
conversion.
Divide by 3.26.
So basically, you can go out to in the sort of Mather concept, if we call it that. You can go out to 20 parsecs, so let's say 60 light years.
Wow.
And with the Earth trailing one, you can go out to 50 parsecs, so something like 150
light years. And there's at that point now you're looking at millions of stars, and
it depends on how you select them, of course.
Yes,
but you're certainly looking at hundreds of well-suited sun-like stars in this strip that I was talking about, and of course thousands more outside of this strip. Yeah.
That's very cool. So then, like, what about budget? What do you think, if people done a preliminary budget of how expensive it would be? Would it just literally just be as expensive as launching a Starshade that would go with, James Webb or go with, say, HabEx or some other mission like that?
Well, so this is always the dilemma, right? Is that nobody actually knows.
Yeah. James Webb, the billion-dollar
Exactly.
spacecraft, the billion-dollar James Webb spacecraft
Yeah,
that will
exactly.
launch in the year 2010.
Yeah. I think there are certainly prospects for the Starshade alone with a telescope on the ground to be cheaper than. I mean, so I think certainly if you're sort of comparing apples to apples in terms of the science case, so what you can actually do with the mission, and then you can always think about scaled down versions, and that's usually easier to do. Like HabEx, for example, is an example of what I would call a scaled down version of something like LUVOIR, which is a sort of more ambitious Starshade type mission. Then you can probably get away cheaper in space, but then you're very limited in terms of what you can do. So there's always going to be this sort of trade-off and a huge uncertainty factor really in what the cost would actually be, because I mean, it really is the case that when you're doing something new like this, I mean, you can always make estimations, but you have to be prepared that it can be a factor of several.
Right.
Wrong.
But it does feel like, when you're looking at, say, a mission like HabEx or a mission like LUVOIR, you've got to launch both the telescope, and the telescope's got to unfold or be constructed in space. You've got to launch the Starshade. The Starshade's got to arrive at its destination. If either half of this doesn't work, then potentially the mission itself is not going to do its job. But in this case, you've already got a beautiful working, extremely large telescope, and all you've got to do is launch an occulter. And I'm guessing you could even sort of make your way towards it. Start with a smaller occulter that's maybe closer, or figure out a way to sort of split the difference until we've mastered this technology. Because it's still even theoretical. I mean, we don't even know if these occulters are going to work the way the math says they should until they're out in space. And there's no way to test on Earth.
No, exactly. I mean, you can do lab tests, of course, but it's not going to give you the full story of how it actually behaves in space.
Yeah.
No, that's right. And I mean, it's really, I mean, if you just think of, okay, what's the most expensive part of the JWST? I mean, people might think it's the cost of launching the telescope or something like that. But it's really the testing and the integration of the telescope, because it has so many moving parts and so many things that have to work perfectly in a telescope optical system, that if you want to make sure that it works perfectly, that's an enormous task, and it's enormously expensive, as we've seen with JWST. And all of that is basically gone if you're using a telescope on the ground, because it already exists. You know it exists. You know it works.
Yeah.
You know if it breaks, you can fix it. So it certainly has the potential to be a lot cheaper and a lot more robust.
And could you scale the idea down with a smaller telescope? So if you had, if you cast a smaller shadow with a smaller starshade, then you could use a smaller telescope.
Exactly. That's exactly right. So in this paper that I published now, which was basically ESA, the European Space Agency. Sorry, this is a little bit of a sidetrack from your question, but I'm just setting a bit of a background. So the European Space Agency made a call for ideas, basically. They're called white papers. So you send in white papers with your concept and how it would work and so on. And when that process was starting to finish, they sort of asked those of us who had written white papers to write an article about it to be published. So I wrote this paper, which was the one you referred to in the beginning that you saw. So in that paper, I discussed this, and basically my line of thinking there was, okay, if we really want to, for example, show that starshades work just as a concept, and do some, also do some really cool science with it, like what's the cheapest and what's the most simple thing that we can possibly do. I mean, because of course, you could just send out a starshade and not really have much of a science objective, but that would be expensive, and it would be very hard to rally people around this thing if you're not actually going to observe something that's actually scientifically interesting. So yes, so then what I came up with is that the cheapest thing certainly that I can think of is to basically observe Alpha Centauri, only Alpha Centauri, but both stars. And so basically what you need two starshades for this, but the starshades can be quite small. So together, it's very fair to say that they would cost a lot less than one of these big starshades that we're talking about, both in terms of, in terms of everything, in terms of launching them and everything. You don't need to worry about lots of the caveats that I've been talking about, like going from one star to the next star,
right?
Which is the most expensive maneuver.
Because you're just getting a chance to observe it with every orbit.
So in this Alpha Centauri case, basically what you're looking at is a one-shot option. So you launch your two occulters in a highly eccentric orbit, so something similar to the mother concept, and then you have one shot, but you take that shot when the starshades are at the maximum separation from Earth in the orbit, and then you can very easily get them to stay there for 1 hour.
Wow.
So you and then you observe with a VLT, which you can fit into the shadow of these occulters. The VLT has a fantastic instrument that's called MUSE, which already exists. So there's zero speculation here. That's an instrument that exists, and we know exactly what it can do. And with that, you can get, if there's an Earth-like planet around Alpha Centauri A or Alpha Centauri B, you can get an excellent spectrum over basically all of the visible light range, and you don't need to send up any telescope, right? You only need to send up these starshades, which are based also on technology that people have worked on a lot by now. I mean, NASA have been putting a lot of thoughts, because they're thinking about this HabEx missions and things like that, just into the starshade concept in general. You can just use a concept that already exists. And as far as I could foresee, I mean, I'm not an economist, but everything comes together to something that I think would be actually quite cheap.
Would you get, I mean, with an hour of observation time, would you get kind of a snapshot of the whole system, like every bright planet that's orbiting Alpha Centauri?
Yes. I mean, you would get, I mean, if you had an Earth and a Venus, you would see the Earth and the Venus, for example.
And the Jupiter.
Jupiter, sure. I mean, we have pretty strong indications that there's no Jupiter, because people have been doing rate velocity measurements of the system, and they would have seen Jupiter most likely. So there's probably no Jupiter hiding there, but there could be like a Neptune or something like that. Let's say you had a Neptune at 3 astronomical units or something, you could easily see it. Yeah.
I mean, one of the things that I'm always really fascinated by is when spacecraft outlive their original design parameter. Spirit and Opportunity, instead of doing 3 months, did years. And so there's got to be ways that you could use those spacecraft after they took their one shot, gave you an hour of observing time. I mean, they're going to naturally wander in front of other things. We see natural occultations all the time that astronomers use to observe the atmosphere of Pluto, things like that. So would you still have other random things that you're going to be keeping track of them and seeing what they're occulting, and maybe something interesting will happen?
So it's not a sort of plan that has been actively pursued. I mean, so if we're thinking about this sort of scaled down Alpha Centauri mission that I mentioned, you really literally only have one shot, because you're sending it up in such an elliptical orbit that the closest passage is inside of the Earth's atmosphere.
Oh, so they just crash back into the Earth when they're done.
Right back.
Yeah.
For the other concepts, I mean, you're still going to have the occulter out there, but the problem is that you really have to, if you don't have the fuel to decide where you're going to be at any given time, it's a very small probability that you line up perfectly with something. I mean, you could always think about stuff like, if you have a space telescope up, you could maybe you could line that up with a shadow or something like that. it's a difficult problem, I would say.
Right. I mean, I sort of think of, like, on the one hand, you have examples of, say, the Chandra X-ray Observatory, where they just, as the telescope was slewing from position to position, they were just gathering all the photons from those slews, and they were eventually able to build really interesting maps of the X-ray background radiation of the entire galaxy. But another sort of more extreme example is, say, gravitational microlensing, where you detect exoplanets because two stars have perfectly aligned up, and you will never be able to observe those planets again because you needed those two stars. And so I'm sort of envisioning these situations where you've got ground telescope, occulter, star system that's at the right distance, but also the right sized occulter, and that everything is lining up. I guess you just can't get those because the math is so remote. You're not going to get a lot of useful science unless the occulter is exactly where you want it to be.
No, exactly. I mean, so basically, it's your kind of, if you're imagining kind of, shooting a laser or something at a star. I mean, that sort of sets the line that you have to line up. And you really have to point that laser, so to speak, very accurately to really get an occulter really in front of the star. But I mean, something that you could. This is just actually something that when you were talking, I was thinking about it now. I mean, something that you could do if you're talking about reusing. I mean, say you're launching one of these concepts, and it turns out really successful, and the occulter is still out there. I mean, you could think about just going up there and refuel it. Mm-hmm, mm-hmm. Going up with a servicing mission, like the servicing mission that they've done for Hubble. I mean, basically what happened, right, was that they had to service Hubble in the end. And they wanted it to work. So they went up and did it. And then they've serviced it several times to upgrade instruments and so on. Because it's been such a success, right? So once you're in that position where you really have a successful mission, probably you could have the opportunity because it's going to be there, so you might.
Yeah, I talked to the people from working on the James Webb, and of course there are no plans to refuel James Webb, but at the same time, James Webb, on the bottom of it, it does have the docking port that's used to attach to its upper stage. It does have the fuel lines that run through that in order to fuel it up, because they fuel it up as they're getting ready to launch it. And so once James Webb is out there in space, it still has all this hardware configured onto it. And if you did send a follow-on module, you could refuel James Webb. And I would imagine the exact same situation with this mission, that it's going to have all of the fuel hardware, mounting hardware that was used. And so in theory, you could send a spacecraft to go and refuel it from time to time. I mean, but we could say that about a whole bunch of missions. I mean, I think we're going to enter an age where refueling spacecraft becomes, with large reusable spacecraft, say with Starship and so on, that maybe things do become a lot less expensive to be able to refuel, and it becomes much more feasible to think about these things as lasting for much longer periods of time as opposed to one shot. I mean, just hearing the one shot just makes me feel sad. Because, an hour of observing, mapping out all the planets at Alpha Centauri sounds wonderful, but then knowing these things are going to crash back into the atmosphere just makes me sad.
Yeah.
But there's
and it would be. I mean, it's if you're thinking about something like the mother concept, it would be a lot easier to refuel than something like the JWST, because it's in an Earth-bound orbit.
Yeah.
Whereas JWST is in a so-called Lagrangian orbit, so it's much farther away from.
So how has the reception been for the concept, especially getting Mather on board? That's got to help with some star power.
Yeah, I mean it's very mixed, I would say. I think people are either very enthusiastic or they say can that really work? And so I think it's what you really need is more studies, exactly what NASA is doing now. I think, as you say, right, the fact that you have someone like Mather on board means that you have a channel through which you can actually develop these concepts properly, which is really what we need. It's because as a physicist, we can come up with ideas and we can check that they work in theory. But in the end, there has to be an interplay between engineers and astrophysicists to get the thing to work, right? And that has to happen at the space agency level. So either at the European Space Agency or at NASA or some other.
Have you proposed it for a NIAC grant through NASA?
No, I have not. I'm sort of expecting that's a channel that
Yeah.
John would
Yeah, a few $100,000 to take a look at it. So yeah.
yeah.
Very cool.
It's a bit of a problem there in my experience is that if you're trying to do sort of European US collaborations on these kinds of sort of engineering astrophysics matters, it becomes very difficult because the US has a lot of restrictions in terms of which information they are allowed to give out.
Yep.
To non-US citizens. It's just as a brief little anecdote, after I published this paper in 2007, which was my first study on the subject, several people contacted me and said, we should send in some concept idea to ESA about this. There was a call for proposal, so I started collaborating with some Americans, and we had a meeting, and I basically said, they asked me, could I lead the proposal? And I said, sure, I've never done that before, but I can try it. And in the first meeting, I basically said, I'm going to need the mass and an approximate cost of this mission. And they said, well, we're not really allowed to tell you that.
Yeah.
So that at that point, I kind of threw up my hands and said, okay, this is for someone else to try.
Yeah.
But it is very difficult. So I think if it's going to be done, it's going to be done sort of within the US or within Europe, and then when you have a developed concept, then you can have joint missions and things like that, because that's a lot easier.
That sounds cool. My you know what? My money's on the Japanese. That's who I would take the proposal to. I am so fascinated by all of the cool missions that the Japanese are working on. They're willing to really try out wacky ideas, and I think, they've got the Subaru telescope. It's the right size. I think this is your shot. Go talk to the Japanese. Well, Dr. Janson, it was an absolute pleasure to talk to you. I put me in the enthusiastic camp. I'm pretty excited about what you're proposing, and I am really looking forward to the progress that you make. If people want to follow what you're working on or keep track of the project, where should they go and keep an eye on it?
Well, so I would say the first thing would be to just read the paper that's out there. I mean, it's on the archive. That's those of the readers who are scientists will probably know that resource, but it's also available through open access.
Yes.
At the Experimental Astronomy Journal.
Yeah, so I'll put a link in the show notes to the actual link to the paper, and as I said, as you said, the paper is open access, so anyone can go and read it, and it's a very readable paper. It goes into some math, but you get the gist of the conversation as well, and it's an absolutely fascinating conversation, and I'm really looking forward to anyone putting up a Starshade at some point in the future. So, Dr. Janson, thank you so much for taking the time to chat with us today. Really appreciate it, and good luck with your mission.
Thank you.
Thanks.
Thank you very much. Bye.